Welcome to the Space Telescope Public Lecture Series. Today's talk is on the Nancy Grace Roman Space Telescope with two special presenters, Jennifer Wiseman and Julie McEnery of the NASA Goddard Space Flight Center. I'm Dr. Frank Summers of the Space Telescope Science Institute, and it is my pleasure to be your host. And I want to note that our public lecture series will continue to be online only until further notice. Also have to thank our amazing tech team who gets you this online version of it, Thomas Marufu and Grant Justice. They do amazing things behind the scene, and I really appreciate their work. Upcoming. Next month on November 10th, that will be a special date. I should have added that special date there because Election Day is, of course, November 3rd. There will be no public lecture series on Election Day. Instead, the week after, on November 10th, Hearing the Light, How Sonification Deepens Our Understanding of the Cosmos and Makes Astronomy More Accessible. That, I think, is probably another candidate for one of the longest titles we've had, but Scott Fleming, Clara Brasseur, and Jennifer Kotler will explain it all to you. They've got this great program called Astronify, and they'll give you all the details next month. In December, Mitchell Rovalsky will be talking about shaping galaxies with supermassive black hole winds. The supermassive black holes at the cores of galaxies can actually change things on galactic scales. It's really cool, and he'll tell you about that in December. And then in January, another special date, because we have the New Year's, and then we have the AAS meeting, and the AAS meeting is going to be late this year, so we're pushing it all the way back to January 19th for the darkest secrets of the universe. You're definitely going to want to hit this one. This is a friend of mine from UC Santa Cruz, Raja Guthatkirta. He's an amazing speaker, and you're definitely going to want to see that. If you want to keep up with the public lecture series and what's coming up, go to our website, stsci.edu/public-lectures. There you will find the webcasts. On the left, you can see that we have links to our YouTube playlist, as well as the webcast archive that they handle here at the Space Telescope Science Institute. And on the right, you can see that you can subscribe and get our lecture announcements, which is basically 2 emails per month to remind you of the upcoming lectures. Also on the website are the details of the upcoming lectures. Usually about a month before, we have a detailed abstract that's put on there. And if you click on each of these, especially after they have been gone, you have the complete details of the lecture, as well as a link to view the webcast both on STSCI and on YouTube. For email, as I said, the announcements, it's easiest just to sign up on the website. But if you want a different reminder, you can also subscribe to our YouTube channel, youtube.com/Hubble Space Telescope, all one word. You'll get the notices not only of these live events, but also when we post new videos, which we do on a regular basis. Finally, if you have comments or questions, you can send them to the email address publiclecture@stsci.edu. You can also follow us on social media. We have social media accounts for the Hubble Space Telescope, for the James Webb Space Telescope that launches in 13 months, and for the Space Telescope Science Institute in general. Facebook, Twitter, YouTube, and Instagram. I myself do a tiny bit on Facebook and Twitter, and you can follow me there. Now, our news from the universe for October 2020. The first story tonight, illuminating the gaseous halo of Andromeda. So they often say there's more to the universe than meets the eye, and that's oh so true in astronomy. So let's give you an example of this galaxy cluster. This galaxy cluster is a name of MACS J0416.1-2403. Not all things in astronomy have fun names. This one just happens to have its catalog name. But this is the view in optical light, visible light. This is as how Hubble sees it. But if we add to this the view from the Chandra X-ray Observatory, then you can see that there is a lot more to this cluster than meets the eye. The X-ray shows up this hot gas that permeates the cluster and spread throughout the cluster, and that there's this intra-cluster medium, that there is more to galaxies than just what we see. There's a lot more stuff. There's a big gaseous halo of stuff around the cluster of galaxies. Now, when galaxies gather together into these clusters, the cluster gas heats up to hundreds of thousands to millions of degrees, and it glows in X-rays. And that makes it easy to spot this extra material for these clusters. But what about an individual galaxy, like the Andromeda galaxy? This isn't part of a cluster, it's just part of our local group, and the local group isn't mixed up and all the gas is heated and everything. So how are we going to find the halo of material around Andromeda? Well, let me first state that I'm not talking about the stellar halo. This image here, and you can see that tiny little box there, that's this blow-up image of that tiny little box that's well outside the main part of the galaxy. We call that the stellar halo of Andromeda, and that's the stars that orbit around Andromeda that are still part of the galaxy, that are still bound to it, and that's relatively close in for the halo that we're talking about. The halo that we're talking about is the gaseous halo of Andromeda, and it extends out like 10 times further than the galaxy itself. We want to figure out, is there gas like around that cluster of galaxies extending way, way out into the universe? But how are we going to do that? It's not glowing at X-ray wavelengths, so we need something to illuminate it. And what do we use? We use something called quasars. Now, the term quasar used to mean quasi-stellar radio source, okay? And you can see these 5 objects here. These are what look like stars, but they're actually supermassive black holes at the cores of galaxies shining across the universe. So these are very distant galaxies with extremely bright sources in them, and they can be used as sort of like flashlights to look through the stuff in between us. So what they did is they went out and they found 43 quasars in the area around Andromeda. And they examined the light of those 43 quasars to see if they could see the gas around Andromeda absorb some of the light of the quasar, affect the light of the quasar. They studied it with the cosmic origin spectrograph in ionized carbon, silicon, and oxygen to try and understand the density of this gaseous halo out to distances. And what did they find? Well, it's sort of illustrated in this diagram, but they found that there was an inner halo that's really disruptive and dynamic and active, and it's probably disrupted by supernovae going on in the Andromeda galaxy and the various things, the dynamics of happening inside it, as well as there was an outer halo, an outer gaseous halo that was calmer and actually was warmer and hotter. All right, and so you're looking in all of these lines of sight, they were able to actually get a radial distribution and find that there was an inner halo and an outer halo. And in fact, that outer halo stretched for 1.3 million light years away from the center of Andromeda. Now, if you know Andromeda, it's only 2.5 million light years from the Milky Way. That's half the distance, 1.3 million light years of this gaseous halo. So if the Milky Way has a similar size galactic halo, then the 2 gaseous halos are close to touching now. They're close to overlapping. You know, the 2 galaxies themselves, they won't collide for another 4 billion years, but it looks like the gaseous halos might actually get close to touching relatively soon. So this is a great study looking along these 43 different lines of sight in order to find out the gaseous structure of the gas around the Andromeda galaxy. And this is a cool image. This is an artistic view that if we could see that on the night sky, just how huge this would be. It would extend approximately 40 to 60 degrees across. And that would be quite a sight, certainly the largest thing on the night sky. Our second story today, do you like your dark matter smooth or extra chunky? Now, that's usually the question people would ask about peanut butter, but actually I've been able to twist it and make it apply to dark matter. So let's go back to that galaxy cluster that I showed you, okay? And there you see the visible light with the X-ray light overlaid on top of it. But if I take off the visible and I only show you the X-ray, you can see that the X-rays are relatively smooth. And the X-rays have been traditionally taken as a proxy for the distribution of the dark matter in these clusters of galaxies. So there is a little bit of substructure in the X-rays, but basically we've sort of assumed that the dark matter is relatively smoothly distributed around these clusters of galaxies. And actually it's been a sort of study for years, how much substructure is there in clusters of galaxies. But X-rays aren't the only way to measure where the dark matter is in a cluster of galaxies. You can also use something called gravitational lensing. And this is another galaxy cluster, MAX J1206, and it exhibits these gravitational lensing. Now, gravitational lensing is an outgrowth of general relativity. And if you've been listening to me, you probably know what I'm going to tell you. It's my 3-word summary of general relativity. All you really need to know about general relativity in 3 words. Ready for it? Mass warps space, okay? That's what you need to know about general relativity. And it's demonstrated in this cluster of galaxies by these 2 images. And the mass of this cluster is so massive that it has warped the space, and the light from galaxies passing through this warped space has become stretched out and formed these arcing streaks across the image. And these very large arcs and streaks are indicative of the large scale distribution of matter. And from these gravitational lensing, you can understand the total mass in the cluster. But what they wanted to do was study the substructure, how much detail is in there. So they went looking with Hubble on several of these very large clusters to try and find out how much detail is there and how much clumping of matter. Right? And so here are 3 examples from the exact same image of small scale structure, small scale gravitational lensing events that indicate matter is clumped on smaller scales, not on the whole scale of the cluster, but on subclumps within the cluster. So here we're seeing the individual lenses at very small scales, indicating there's a lot of dark matter clumped in there, right? So the conclusion was that it was extra chunky, that compared to the previous observations and compared to the simulations they do of galaxy clusters, that there was 10 times more small scale lensing, or the strength of the small scale lensing was 10 times more than they had anticipated. So if you go back to the X-rays, you've got your smooth distribution of dark matter. But if you go to your small scale gravitational lensing, you get your extra chunky version of dark matter. And which one of these is correct? Well, they're both going to be correct in some scales, but we need to, of course, do more study. This has brought up the idea that maybe there's some clumping on smaller scales than what we've heretofore assumed in dark matter. And we're going to we're going to investigate it more. And I'm told that the Nancy Grace Roman Space Telescope will be able to add to this. I'm not exactly sure how. Maybe they cover it in the talk today. But this is a really cool result in terms of what is the status of the dark matter on smaller scales than clusters in the universe. All right, so that's our news, and now let's go to our speakers today. Our first speaker today is Dr. Jennifer Wiseman of the Goddard Space Flight Center. She is the Senior Project Scientist for the Hubble Space Telescope mission at Goddard. She is also a Senior Astrophysicist at Goddard Space Flight Center. She studies star formation, and she really, does that across the spectrum. She's, looking at many different wavelengths in order to study the process of how stars were born. She herself, she tells me she was born in Arkansas, in the Ozarks in Arkansas. And she has a special merit to her name in that she discovered a comet back in 1987. So Jennifer, if you would start your screen share, ladies and gentlemen, Dr. Jennifer Wiseman.
Hi, okay, let me see if this will work. I'm glad to be here today. and we have a lot to talk about. All right, so is that working?
Yes.
Okay. Today we are talking about a new telescope, a major observatory that NASA is developing right now. It's called the Nancy Grace Roman Space Telescope. And yet I'm going to tell you a little bit about the background behind the Roman Space Telescope that has to do with what I work with, which is the Hubble Space Telescope, and the namesake of the Roman Space Telescope, Nancy Grace Roman. So how do all these things fit together? That's my job. And then after me, Dr. Julie McEnery will tell you more about the details of the Nancy Grace Roman Space Telescope and the science that it will achieve. But my work with NASA is with Hubble. And if you want to know more about Hubble, we have wonderful website, nasa.gov/Hubble, and we're active on social media at NASA Hubble. How does Hubble relate to this new observatory being developed, the Nancy Grace Roman Space Telescope? There's a kind of artist conception of what the Roman Space Telescope will look like. Well, let's talk about this fantastic person after whom this new telescope is named, Dr. Nancy Grace Roman. Sadly, Dr. Roman passed away a couple of years ago, but her light still shines on our world, and in particular on the astronomy world and the astronomy enterprise that she really set the foundations for. Let me tell you a little bit about this fantastic person. Who was Dr. Nancy Grace Roman? Well, she herself was an accomplished astronomer and really a pioneer in the field. She was the first woman on the astronomy faculty at the University of Chicago, which is a powerhouse for astrophysics. And then she became the first chief of astronomy and also solar physics at NASA. I mean, this is remarkable. This is right toward the very beginning of the agency as a whole. And they were just setting up, what would be NASA's role in science? And she held that first position. She was the first woman to hold an executive position at NASA. So really a brave pioneer. But in that role, she was a driving force to build the foundation and the execution of NASA's space telescopes and a lot of NASA science. In fact, a lot of people don't realize that the Hubble Space Telescope is not the first space telescope. There was a group of telescopes called the Orbiting Astronomical Observatories and even Orbiting Solar Observatories. And Nancy Grace Roman was the driving leader behind these observatories, these OAO observatories that were kind of experiments. Could we do astronomy from space? And that set the stage for Hubble. She was also instrumental in a space telescope known as the International Ultraviolet Explorer. And she was involved with other types of space-related science experiments that were on Gemini, Apollo, and even Skylab. She was instrumental in establishing a whole new era of space-based astronomical instrumentation and research, the kinds of things we depend on now for doing the kinds of astronomy that we take for granted now that can be done from space. We need instrumentation to be able to do that. But she's most well known for being the powering force, the figurehead at NASA that really pushed the idea of a large space telescope that became the Hubble Space Telescope. So she's affectionately called the mother of Hubble. And we still so much appreciate Dr. Roman. She, because of that, was the recipient, and all her work was the recipient of NASA's Exceptional Scientific Achievement Medal, amongst many other awards. And throughout her lifetime and career, she was a champion of women in astronomy and a strong advocate of STEM for all young people and people considering careers. So this is an overview of this inspirational person. And I had the privilege of meeting Dr. Roman in recent years. And she was just as inspiring to me in these last years of her life as she was to people decades earlier. Let me explore a little bit more into her life and her contributions. Dr. Roman told us that she was born curious back in 1925. And she attributes a lot of her interest in nature and in space to her mother. Her mother encouraged her to go outside and look up, to go stargazing, to look at the auroras. Even at a very early age, she was given books about the sky and looking at stars. Her father was a scientist and, encouraged her to play kind of mental math games, things like that. All these things from her parents really encouraged her to think about the natural world, to go into science. And even at age 10, she started an astronomy club. And by age 12, she decided that she wanted to be an astronomer. And so she did. She was undaunted by the fact that astronomy was really not considered at that time to be an appropriate career for a woman, an appropriate life path, but she went on anyway, got her bachelor's degree at Swarthmore College, and got really on fire for the field of astronomy in her college years in the 1940s, went on and got a PhD from the University of Chicago, and worked at the Yerkes Observatory, which is affiliated with the University of Chicago, performing forefront research that actually landed one of her research papers as one of the 100 most important astronomy papers. She was an assistant professor at Yerkes and really led the field as a research scientist for many years. But about that time, later on in her career in the 1950s, the NASA space agency was being formed, and she was asked by one of the people helping to formulate what this new agency would be like if she knew anybody that would be interested in developing a space science program within NASA. Given that women didn't have a lot of opportunities to become tenured professors in astronomy those days, she decided she would take this on. Asked if she knew anyone who would want to set up a space astronomy program at NASA, she said, yeah, I would. And she was given that chance. So she became the head of observational astronomy way back in 1959 and was the first formal chief of astronomy starting in 1960, right at the birth years of NASA. And in her role there, she worked very hard to establish a strong foundation for science at NASA that still remains. She was the driving force behind these first space astronomy observatories that I mentioned, and also solar observatories. And she also became very adept at advocating for space astronomy to the powers that be, to scientists, to industry, to politicians, to government leaders, to even the government budgeting offices. She knew how to make the case that space astronomy would be effective and it would be important for the nation. To get telescopes above the Earth's atmosphere would give us a clearer view of space beyond and would help us develop technologies that we could use in many aspects of our national technological growth. So here you see a couple of pictures of Dr. Roman at NASA. The one on the right is with the orbiting solar observatory that she helped develop as well. She is, however, most well remembered for her advocacy for a large general purpose space observatory, larger than these preliminary orbiting astronomical observatories. This was something that became her passion. She worked with the scientific community, including Dr. Lyman Spitzer, who's now kind of known informally as the father of the Hubble Space Telescope, and he, at her instigation, led a National Academy of Sciences study on the scientific uses that could be gleaned from having a large telescope in space. And it was this kind of thing that started to drum up the popular support not only in the public, but primarily initially in the scientific community and in government, for putting an observatory on a space platform that could be a general purpose observatory. And eventually that led to a real solid opportunity that she put together, the first announcement in 1977 of an opportunity for scientific participation in a large space telescope mission, which was later named the Hubble Space Telescope after astronomer Edwin Hubble. Now remember, there had to be a lot of thinking about this. We now take these space observatories for granted, but there were lots of different ideas floating around. So just as an aside, I want to show you one of the initial schematics of what a space telescope might look like back in the 1960s. And if you'll notice in this picture, the astronomer is actually there inside the telescope, orbiting the Earth. Now, wouldn't that be fun? As somebody who works with the Hubble Space Telescope mission, I wish I could actually go there and be there in person if I had the appropriate spacesuit. But it was soon realized that this was impractical and unnecessary, that you could transmit commands to the telescope remotely from the ground and then bring the data back from the telescope to the ground. So lots of ideas had to be worked through over the years, but eventually in 1990, the space telescope, the large space telescope idea was realized. It was launched into space on the space shuttle successfully, based on all that foundational advocacy and wisdom and expertise of Dr. Nancy Grace Roman. And now, of course, we are celebrating the 30th anniversary of the Hubble Space Telescope. We're now spoiled on all the investigations and the images Hubble has given us, everything from the solar system to nebulae and to galaxies and deep space as a general purpose observatory. Dr. Roman has received many awards and recognition. Some of them include the Federal Women's Award in 1962, and you see the picture there on the left with President Kennedy. She's received many awards from NASA, including the Outstanding Leadership Award and the Exceptional Scientific Achievement Award. She received a Women in Aerospace Lifetime Achievement Award and 3 honorary Doctor of Science degrees. And there she is in the lower right, in recent years, talking with Nobel laureate Dr. Mather. That should be John Mather, not James Mather. And of course, her favorite award was that she was the model for a Lego set honoring women in science and women in space related careers. So there's Dr. Roman at the Legoland Discovery Center in Boston, and on the right there with Margaret Hamilton, and they're at home proudly showing off her Lego award right there in her hand. So you can, I think, still find this. If you look carefully, you can find your own Nancy Grace Roman Lego kit. All through her life, not only when she was working at NASA, but for all these years later, she's inspired people of all ages. She made it part of her life's mission to encourage people. So you see in these images, even from back in the 1960s, she met with students to encourage them. And then decades later, she's still showing up at NASA Goddard Space Flight Center, where I work, to encourage the Hubble team. That's us down there in the lower center. And there's a fellowship named after her now, the Nancy Grace Roman Fellowship, with one of the recipients of that fellowship for technology work in the upper right. And the lower right, there she is at a school encouraging young people. So she continued her interest in space science, showing up at colloquia all the way through the end of her life and encouraging people, young and old, in these kinds of pursuits. And there she is getting a crystal Hubble from the Goddard Space Flight Center Center Director a few years ago, and encouraging women who work with the Hubble mission even now. There in the lower right and in the upper left, she seemed to be enjoying being in the Hubble control room on camera as we interviewed her and got some of her thoughts and reflections on the space program recorded. So Nancy Grace Roman set the foundation for space-based astronomy, particular the Hubble Space Telescope, and now that has led into many other space telescope platforms, including the Chandra X-ray Observatory that's still operating very well, the James Webb Space Telescope that will launch next year, and the Nancy Grace Roman Space Telescope, which you'll be hearing more about today. And I like this quote from her where she says, "I'm glad that I ignored the many people who told me I could not be an astronomer." We're glad too, Dr. Roman. All right, just a couple more words about space telescopes. The Hubble Space Telescope is fantastic because it is orbiting above the Earth's atmosphere. It gets the sharp images, such as this clear view of a very crowded star cluster, Omega Centauri. You can differentiate star from star because the angular resolution is so good. We're not affected by the blurring of Earth's atmosphere. We see the beauty and the scientific detail and differentiation between stars in crowded regions like this. And we're celebrating Hubble's 30th birthday because Hubble has been kept in tip-top shape. Astronaut servicing of the Hubble Observatory, time and time again over the years, has enabled repairs, enhancements, and mission life extension. So we actually expect Hubble to keep operating for quite a few more years to come in this decade and perhaps beyond. And this is good news for science because we have new observatories coming online, and Hubble cannot do everything. Neither can the other observatories. These are complementary observatories. We're accustomed to these beautiful images from Hubble, like the 25th anniversary image here of a massive, recently formed star cluster, Westerlin 2, with its birth nebula, and the 30th anniversary image of another star-forming region and a star in the lower left expelling its outer atmosphere in our neighboring little sister dwarf galaxy, and even looking at other galaxies in spectacular detail. But Hubble has a quite small field of view, meaning the area in the sky that Hubble sees is not very large. So here's a comparison of the field of view, that kind of swath of the sky that you can see in one pointing, with Hubble down in the lower center there, that little blue box, compared to Roman, which is that big kind of funny shaped red outlined area. In the background there is Andromeda. We've already heard about the Andromeda galaxy from Dr. Summers, but that's a region that Hubble has imaged, but it took Hubble hundreds of pointings to cover that region of the Andromeda galaxy, and to stitch all those images together. Roman could look in just a couple of pointings and see that area before you. Here's another way of looking at it to scale with the moon. There's the Andromeda galaxy with the moon to scale next to it to just show the size scale. And if you look carefully in the upper left, you see that little red footprint there. That little square is how much that Hubble can see in one pointing. So to cover even a big chunk of this galaxy and make a stitched together image, Hubble had to look at do hundreds of pointings. But the Roman telescope will have a field of view 100 times larger than Hubble's. And so as you see, if you look at that little area in the middle covered by the little white squares, all of that together is what Roman can see in one pointing. So the Roman footprint is bigger. It's more efficient at looking at wide swaths of the sky and looking at surveying large areas of the sky. So Dr. McEnery will explain why that's important to us. There's another comparison, which is the wavelengths of light. So if you look at this image, you can compare the Hubble telescope mirror on the left. Its 2.4 meter mirror is the same as that for the Roman telescope, which used to be called WFIRST. And the Webb telescope's mirror diameter will be much bigger, 6.5 meters. It'll be very sensitive. But if you look at the bottom there, you'll see the different kinds of light that these different telescopes pick up. So you see wavelengths of light in that rainbow, all the way from ultraviolet light through the visible range of the spectrum and on into infrared light. And you'll see the Hubble range there underneath that. Hubble sees into ultraviolet part of the spectrum, all through the visible piece, and a little bit into the infrared part of the spectrum. The Roman telescope will see some visible light and also into the infrared part of the spectrum. And the Webb telescope will see much deeper into the infrared part of the light spectrum. So if we compare the different capabilities of these observatories in terms of the wavelengths of light that they see and the fields of view that they can pick up, you see that these telescopes are complementary, and they can do complementary types of science that will really help one another. So we're very excited in astronomy that it looks like later this decade, we'll have the Roman Space Telescope as well as the James Webb Space Telescope and the Hubble Space Telescope operating at the same time to give us complementary information, each providing capabilities that the others cannot provide. So with that, I hope you've enjoyed this introduction to the Nancy Grace Roman Space Telescope, telling you a little bit about the fantastic namesake, Dr. Nancy Grace Roman, and how she inspired the Hubble Space Telescope, which has now set the stage for these subsequent space observatories that are opening new vistas for us on the universe. I thank you very
Jennifer.
much for your interest, and I'll hand it over now to our next speaker, Dr. Julie McEnery.
All right. Thank you, Jennifer. That was great. If you could stop your screen share and let Julie start hers. What I really liked about your talk, Jennifer, was that you get the impression that, Kennedy was sort of the vision that talked about we're going to the moon and everything. And here you've highlighted the fact that it's Nancy Grace Roman, along with Lyman Spitzer, who sort of act as the scientific visionaries of NASA during the 1960s, because it's more than just space that NASA was created for. And you've highlighted, I don't want to say unsung heroes, but certainly the ones who don't get as much commentary in the popular press.
Yes.
So. All right, so our second speaker today is Julie McEnery, and she is also a senior project scientist at Goddard Space Flight Center, but she's the senior project scientist for the Roman Space Telescope, as you might guess. She also has her PhD and has a long and illustrious career of science observations, but she likes to talk about extreme explosions. And as we were chatting before this, she said, and she even goes further across the spectrum than Dr. Wiseman does in terms of her observations. You can see in her background, she is from Ireland, having been born in Dublin. Yeah, I'm really looking forward to hearing about the upcoming Roman Space Telescope. Ladies and gentlemen, Dr. Julie McEnery.
Thank you very much. So the Nancy Grace Roman Space Telescope is the next NASA astrophysics mission to be launched after the James Webb Space Telescope. And as Jennifer Wiseman just described, Roman features a primary mirror that's the same size as that on the Hubble Space Telescope, but we have a field of view that's 100 times larger. So I'm illustrating this here with this ground-based image of the Eagle Nebula with the very famous Hubble image of the Pillars of Creation in the center. But something that I want to emphasize is that since our primary feature is having a very large field of view, we're designed to do surveys. We're designed to explore the sky in quite a different way than you do with a narrow field instrument. We've optimized the observatory to be very, very good at conducting surveys. So one example of this is observations of the Andromeda Galaxy. There was a large Hubble survey that was conducted using over 400 pointings. That same set of observations could be conducted with Roman with just 2 pointings. But the point that I want to make is that the Roman Space Telescope is optimized to slew across the sky effectively, to settle and be ready to take observations quickly and effectively. So we spend more time taking science observations. We don't pass through the South Atlantic anomaly. We're not blocked by the Earth. So for this particular observation, we don't do it 100 times faster. We don't do it 200 times faster. Roman could make this observation of Andromeda over 1,000 times more quickly than Hubble. And we use those capabilities to explore the universe in quite a different way, because now we're not so much pointing the telescope at an object that we know about. We can survey large regions of the sky and just see what's there. We can come back to the same patch of sky over and over again and see what changes, see what new transients there are, what has popped up. And I'll describe some of the science that we can get from that later in this talk. But another point that I want to make is that since we've got a much larger field of view, and we're spending a larger amount of our time taking pictures of the sky, and we have the same resolution, we have an enormous number of pixels. Each Roman image is the equivalent of a 300 megapixel photograph. So what that means is that with Roman, we will be sending down an extremely large amount of data to the ground. Our data repositories will need to be extremely large. And we anticipate that this is going to drive a change in how astronomers use and access the data, because the old model of going to a data center and downloading the data and analyzing it on your home computer is no longer going to be the natural way of doing things. And instead, we anticipate that people will log in to the data center and run their software and their analysis routines in place without having to move the data itself. Roman has several mission objectives that drive how we designed this mission. We want to explore dark energy and the fate of the universe. We want to conduct a complete study of the mass distributions of planets around stars. We're going to use our wide field of view and our capabilities in the infrared to conduct a groundbreaking survey across various different places in the universe. And then finally, we'll also have a technology demonstration where we can directly image extrasolar planets. So let me start with the first of these. If you think about what the universe is made of, the matter that we can see, the stars, the galaxies, the dust, us, make up only 5% of what the universe is actually made of. Planck, the CMB observations have told us that around 27% of the universe is made up of this so-called dark matter. This is a type of matter that interacts via gravity, but does not interact with normal matter in any strong way. We don't know the nature of dark matter, but we do know it exists because we can see its gravitational effects on the material around it. 68% of what the universe is made of is of this very mysterious force called dark energy. And it's a repulsive force, and it was discovered in 1998 when astronomers realized that after the Big Bang, instead of continuing to expand and then slowly slowing down, that in fact, the universe was accelerating. And the quantity that causes that acceleration is known as dark energy. So if we want to understand the structure and evolution of the universe, we need to understand both dark energy, because it drives how things are moving away from everything else. But we also need to understand dark matter because it's most of the mass on which gravity acts, so it determines how clustered objects are. So one of the ways that you could do this is to imagine if you go back to shortly after the Big Bang, where the universe is relatively smooth with some small fluctuations that will later grow into being the structure of the galaxy clusters and galaxies around us. As the universe continues to expand, the typical distance between those structures will also expand. So if we can measure the distribution of galaxies as a function of redshift, which is the same as measuring the distribution of galaxies as a function of time looking back into the universe, we're getting some information about how the universe has expanded, and as a result, getting information about the nature of dark energy. Something else that we can do, and this was mentioned in the introduction, is that the presence of dark matter in clusters of galaxies causes the galaxies behind them to be lensed, to be have their shape bent by the effect of passing through the gravitational potential. And if we measure the shape of all of these galaxies and the distance to those galaxies, we can make a measurement of the distribution of dark matter as a function of distance in the universe. And this gives us extremely important information, not just about the structure of the universe, but also about the clumpiness of dark matter. And it's important to understand the clumpiness of dark matter because that in turn can tell us something about the nature of dark matter itself. So with this very large field of view on the Nancy Grace Roman Space Telescope, we plan to conduct a survey that will cover thousands of square degrees on the sky. And in that survey, we'll measure the position and distance to hundreds of millions of galaxies and make a three-dimensional map of the universe. For a fraction of those galaxies, we're also going to be able to precisely measure their shape. And with that, we can get a mapping of the dark matter as a function of distance also. This is something that we can do because we have a large field of view, because we can survey large fractions of the sky. We're not just going to do that one large survey. We also plan to look at a patch of sky away from our galaxy and go back and point there every 5 days. And in that patch of sky, we'll be monitoring hundreds of thousands of galaxies. And if a supernova goes off in those galaxies, we will be able to make a measurement of that supernova. And a subset of supernova are what's known as a standard candle, that we, by making measurements of how the light changes as a function of time, we can infer how bright that supernova really is. So it's a little bit like having a standard headlamp, that if you know how bright the headlamp is, you can tell by how bright it appears how far away it is. If something is far away, it'll appear dimmer. As it comes closer to you, it's brighter. Similarly with these supernova, that we can measure the distance to the supernova by understanding it, by measuring its apparent brightness. We'll see tens of thousands of supernovae. We can measure the redshift to the supernova, so we'll also get a measure of the velocity. So this gives us another measure, a completely independent measure of the expansion history of the universe. And what the Nancy Grace Roman Space Telescope will do, will take each of these three techniques to understand dark energy, dark matter, and modified theories of gravity. Because if the expansion history of the universe is inconsistent with what we see from the growth of structure, it may point to a modified theory of general relativity. To make these observations, we have to have an exquisite ability to measure the shapes of galaxies. We have to have an exquisite ability to measure the brightness of supernovae. So one of the things that we've been very careful of with the Nancy Grace Roman Observatory is designing a telescope that is exquisitely precise. We'll understand the point spread function, the shape that a star makes in our camera, to 1 part in 1,000. We have an ability to translate the intensity that we measure in the detector to our understanding of what that means for the object we're looking at, a factor of 10 better than Hubble. And it's these kinds of things that allow us to take the groundbreaking observations of large swaths of the sky into unprecedented measurements of cosmology. But we don't just look away from our galaxy. We also plan to point our telescope towards the galactic center, towards the bulge of our galaxy. we plan to monitor a region towards the center, 2 square degrees in size. And in that region, there are hundreds of millions of stars that we will be monitoring. And we'll be monitoring those stars, the brightness of those stars, every 15 minutes. And the reason that we're doing that is also related to an effect of gravity. And we're using that, we're looking for changes in the brightness of stars that are produced when another star or another star with a planet passes in front of the background star. So what we will be doing is monitoring a star, monitoring millions of stars, it's rare, but we are looking at a lot of stars. Some fraction of the time, a foreground star with an exoplanet will pass in front. Let's see if I'll play this again. And as the star, the foreground star passes in front of the background star, it acts as a gravitational lens, and it causes the background star to increase in brightness. And you see a second, smaller, sharper increase in brightness caused by the exoplanet that is in orbit around the foreground star. And from this, we can make a measure of exoplanet masses and distances in the icy giant part of our solar system that are currently completely inaccessible to other surveys, and give us a much more complete picture of an exoplanet census in our galaxy. We expect to see thousands of these exoplanets. And I'd like to come back to one of the introduction when we were talking about a desire to understand the clumpiness of dark matter. If there are small, dense clumps of dark matter in our galaxy that happen to pass in front of background stars, we will also see a lensing signal from that. So this technique doesn't just help us find extrasolar planets. This technique will also allow us to find free-floating neutron stars. It'll allow us to find small clumps of dark matter in our galaxy. So I'd like to say a few words about how the observatory works. So light comes in, it hits our primary mirror, which is 2.4 meters in diameter, so around the same size as Hubble. Then it gets reflected back to a secondary mirror. It passes through 2 pieces of optics. You're going too fast, come back. Okay, it goes through 2 pieces, 2 folding mirrors. It then hits a tertiary mirror that is, we require 3 curved mirrors in Roman because the 3rd mirror is required to correct optical aberrations across such a large field of view. The light then continues through a filtered wheel. So we can choose which filter to take the observations to view the universe in different wavebands. And then finally, the light goes through to to our focal plane, which is a set of 18 detectors. And each one of these detectors is 4096 by 4096 pixels wide. So the entire camera of Roman, the main instrument, is this set of 18 detectors that we use to cover the sky. And that's what makes the kind of Space Invader shape that you see when people are talking about Roman. Okay, we've seen that, so let's move on. We've mentioned that Dr. Wiseman mentioned that Roman focuses observations in the near infrared. We do not have the capability to continue observations down to the optical. But that's a good match for the kind of science that we want to do. In the search for exoplanets, we need to have look somewhere where there's a high density of stars. So we want to look towards the galactic bulge, and the galactic bulge is full of dust. And the dust absorption of the light that we're trying to view is much lower in the near infrared than it is in the visible. We're also interested in understanding the structure and evolution of the universe, which means that we want to take observations at large redshifts. At large redshifts, the photons are shifted to longer wavelengths, they're shifted into the infrared. So we really want to make our observations where the photons are. And you can see this in the image at the bottom that shows a comparison of the light from galaxies at a redshift of 2 between the near infrared and the visible. And by making observations in the near infrared, we're improving our ability to be able to measure precisely the shapes of galaxies in that redshift range. Another difference between Roman and Hubble is that the Hubble Space Telescope is in orbit, in low Earth orbit around our Earth. So what you see here is our Earth, the moon going around the Earth. And Roman is all the way out here at L2, the Sun Earth Lagrange point. And what this allows us to do is, in this orbit, it means that the Earth is not blocking the field of view. So we can have those very dense observations, an observation every 15 minutes for months at a time of the galactic bulge. This orbit also allows us to have a region of the sky that is continuously visible for years at a time, so that we can monitor that patch of the sky for several years to search for and characterize supernovae. This orbit also means that we're in a thermally stable environment. And since one of the requirements on this mission is that we have a very precise understanding of our point spread function, that requires keeping every part of the observatory very stable relative to one another. We have a second instrument. The second instrument on Roman is an exciting technology demonstration to directly image exoplanets themselves. And this is an extremely challenging problem. If you have a sun-like star and you have a hot exo-Jupiter, it's the equivalent of trying to distinguish a firefly next to a lighthouse. The problem gets even worse if you're interested in imaging Earth-like planets, because now the light of the Earth-like planet is 1 billion times fainter than the light of the nearby star. So it's the equivalent of trying to find one bioluminescent algae next to a star. That sounds like an incredibly challenging problem. And to solve this problem, we have to find a way of blocking the light of the star so that we can see the planet itself. And we do, this is an interlude. We do this by, with an instrument known as a coronagraph. And to sort of come back to a connection with Nancy Grace Roman, she was actually the first person the author of the first paper to suggest using space telescopes to directly image exoplanets. So this is another example of how visionary she was. So what we do with this is we don't just have a single solid disk that blocks the light of the star. Instead, we put in a complicated shaped mask that uses the properties of light to, along with the block, to cause the light to interfere with itself and produce a dark hole in the center of the field of view that blocks the light of the star. That allows us to see the exoplanet, but that itself would not be sufficient, because small deviations of the optics cause small shifts in the wavelength that will completely wash out the signal, as you see here. So what we have is a set of deformable mirrors. And these mirrors have hundreds of little pistons that change the shape of the mirror to correct for the distortions that are being produced by the optics of the telescope. And this corrects the signal and allows the exoplanet, the faint exoplanet, to be directly imaged. And we can do better with more data analysis to in fact pull out a second exoplanet here. So in this particular system, there are 2 exoplanets. So with this coronagraph, we're going to do a lot of things for the first time. We have ultra precise wavefront sensing and control, which we need so that we can drive the deformable mirrors, which will be the first example of using deformable mirrors in space. We use these complex coronagraph masks that feel, I mean, to me, feels a little bit like physics magic in action. to get an extraordinary ability to see faint objects next to very bright ones. And this is the end of what I wanted to say. I've focused on a couple of science topics. And I focused on our understanding of the structure and evolution of the universe and our ability to find and characterize extrasolar planets. But we're going to do so much more than that. The survey that will find those large number of galaxies is, of course, can study those galaxies too. We'll find many, many quasars. We'll find everything that is changing in those regions. And this opens up an extraordinary amount of science. The precision with which we're designing this observatory will allow us to precisely measure the positions of stars. And as we go back to the same observation time and time again, we will have the ability to measure changes in the positions of those stars and really understand populations and evolution of stars in our galaxy. So I'll stop here with one final comment, is that when the Nancy Grace Roman Space Telescope launches in the middle of this decade, I really hope that the most exciting science result is something that I haven't been able to imagine, something that has emerged because we're using this observatory to view the universe in a different way than we were able to before. That we no longer have to look under a lamppost, we don't have to make so much choices about where to look, we can look somewhere and wait to see what appears. And that I find tremendously exciting. Thank you.
Thank you, Julie. That is tremendously exciting. You know, it's the first time I've seen all those various programs laid out on a single slide, because, you know, when we simplify it to try and explain it to people, and we try and go, all right, there are 3 or 4 messages, right? But I love it that you were able to put that full slide up there, and that's gotten me even more excited. We've had some lively talk on our chat on YouTube, tremendous number of viewers here today. Jennifer, if I invite you to turn on your video and join us, and if we have some questions. And I'm gonna start by asking a question that I wanted to ask about this, is that the data model that we're doing, okay, and in particular with the time domain astronomy that we're getting into, it really is to me this synchronicity of cloud computing becoming such a ubiquitous this decade is really going to help. Do you have any comments on that?
Yeah, I mean, so I think that the upcoming decade is going to be transformational in how we do astronomy. We're entering an era where all data is available to people almost immediately. We're entering an era where the rapid prompt analysis of data and identifying interesting things in those data sets can trigger observations in other observatories, which will open up entirely new possibility in studying things that are varying in the time domain. I think that the model of cloud computing, where the astronomer does the analysis of all publicly available data at a central repository that has lots of computing, is going to be very open and inclusive in the community, because you'll no longer have to be at a special place that has access to telescope time. You'll no longer have to be at a place that has access to large computers. So I think we're going to see the democratization of science. And I think that means that we're going to have more great minds looking at the fabulous data that's coming from all of these observatories. And we're going to have an even better science return, which I also hope I can't predict.
We're always hopeful that we can't predict just how wonderful the results are going to be from these missions.
If I could just add something to that, it is, I hope, obvious from what Dr. McEnery just said, that we need people in the field who are not only experts in astronomy and physics, but we need people who are experts in computers, computer science, data management. That's critical to the successful acquisition and use of all the data that these telescopes are bringing us and will be bringing us. So we need lots of different kinds of expertise.
All right, and we are joined by Grant Justice, who has been monitoring the chat more carefully than I am. Grant, give us a few of those amazing questions that were asked.
Sure, absolutely. I just want to, since we got a little bit of this yesterday during the briefing, I want to say that one of the things that interests me most about Roman is because of the size of the field of view, we're collecting more data kind of in the background per se, and that data will be archived. So even if your star or your observation is not a part of directly what it is pointed at, there's so much more of the sky that we'll be able to use, and everyone, like you said, will be able to use because it's covering so much more area. There'll be this huge repository, which is exciting for the amount of papers that could come out of it, because Hubble already gets a lot and it's such a larger field of view. But yes, wonderful questions. Thank you everyone in the audience for today. This has been wonderful. So will Roman be using our solar system or any of the existing calibrations that we have? I know on Hubble for like single gyro mode, and especially when we have issues, we use guide stars to make up for the positional accuracy when the gyros go out. What will Nancy Grace be using, or do we have any idea at this point?
Well, our main instrument, the wide field instrument, is used to follow guide stars. So we typically pick a section of the instrument to use. We're in a different orbit than Hubble, so that changes some of the things that we can use. We don't, for example, have the benefit of being able to leverage the magnetic field on the Earth. But because we're designed with precision in mind, and because we have such a large field of view, the large field of view means that if we're doing the survey, if we design the survey correctly, we can use observations of different rotations of the field of view with the standard stars there to really nail down very precisely where we're pointing and what the response of our instrument is across the large field of view.
And can I just extend that question to going, I think some people want to know, is Roman actually going to be looking much at solar system objects? We can speak for Hubble, having done the Opal program with its yearly look at the atmospheres of the outer planets. Does the solar system play a large role in Roman's work?
We will have interesting capabilities at the solar system. It's not, solar system observations aren't driving how we're building and developing the observatory. But of course, once we launch, we fully intend to look wherever we're going to get great science. So there are groups of people in the community who are developing the science case for what we could do with Roman in our solar system.
And can we take this question to Jennifer and say, Jennifer, how did the expectations for what Hubble would look at and what it ended up looking at over its 30-year history change over the history of the telescope?
Oh, well, that's a fabulous question. So when Hubble was designed, I mean, there were certainly ideas of what we would use Hubble for, and we have done that, and we continue to, in particular, measuring the expansion rate of the universe. That was a primary goal of for Hubble, and of course people assumed we would be using Hubble to look at the planets in our solar system as well, and we've done that. But by having Hubble working for decades, and including getting improved instruments put on Hubble over the years and innovative techniques of using Hubble, we've started doing things that were not even thought about or imagined when Hubble was designed, like studying the atmospheres of exoplanets orbiting other stars. I mean, when Hubble was designed, we didn't even know if there were planets orbiting other stars other than the sun. And then this whole time domain capability, because if you have a telescope operating for decades, you can look back over and over and over again at phenomena in our own solar system, for example, and see how things change. So getting back to planets in our solar system, we've been able to see things change, such as the weather, the storms on Jupiter are changing. In fact, we just released a marvelous Jupiter image just a few days ago that show how the great red spot, the big hurricane on Jupiter, is shrinking and changing color and morphology a little bit, and new storms are cropping up. And even looking in other wavelengths of light, like in the ultraviolet, we've discovered things like auroras on other planets and things like that. So lots of interesting things, and I haven't even mentioned, but you know, dark matter and dark energy, things like that Hubble has become so keen at detecting the effects of, I should say, were not really imagined as one of the primary possibilities for Hubble when it was designed. So I expect that Roman will be finding things that we don't even imagine yet. And that's part of the excitement of building an observatory with a new capability, or new capabilities, is that, yes, there are some things that drive the passion for building the telescope, some questions you want to answer, but there will be things we haven't even imagined that this new observatory will discover and will inform, you know, our future questions.
Okay, Grant, what's next?
That segues us pretty well into another one, which, how much better is the detector on Roman going to be at discovering exoplanets, finding out information about atmospheres, that sort of thing?
So the detector on Roman, its main feature is that it's larger, which of course is not for any given spot. It's not that much better. It's got a slightly finer pixelization than the equivalent near IR detector on Hubble, but it's not a driving factor. The detectors themselves, the primary difference is that our system is designed to be very, very well calibrated. So we have an understanding, so it's not really a sensitivity issue, we have an understanding of how to translate the light we see in the detector to what we're seeing from the star or the exoplanet, and that we keep that performance very, very stable as a function of time, which means that our ability to interpret and measure very, very precisely the change in star brightness as a function of time to indicate the presence of planets is particularly good.
Okay, that segues me into our next question, which one of the viewers noticed that the visibility bands in the spectrum overlap some. Hubble, JWST, and Nancy Grace Roman will, like, there are areas where they overlap. What is the strength behind that? What is the reasoning behind that? I mean, obviously more than one source, but the audience would like a little more there.
Well, I can give one example of where I think it's going to be useful. I mean, of course, on Roman, we're following in the sort of hallowed footsteps of Hubble. And if we, one of the things that I think is particularly exciting about having Roman follow Hubble and have an overlap in the same waveband range is that we can go and look at the same things that Hubble looked at, but 10 years, 20 years after Hubble made those observations. So Hubble can help provide us with a reference against which we can compare our observations. So we don't have to do it all ourselves. And that's very important if we want to do something like measure proper motion of stars, where having a long baseline really is what's going to enable those observations. So, you know, if at some point in the past, Hubble has spent a large amount of time doing a survey, we can redo that survey very quickly, but we can't leverage anything like the benefit without having that reference from Hubble to compare our new observations against.
And Jennifer, do you anticipate seeing I mean, we've talked a lot, at least at the Space Telescope Science Institute, of doing Hubble versus Webb comparisons against Spitzer and everything, this multi-wavelength astronomy that both of you said were critical to your research. And how do you envision that going forward?
Oh, it's going to be fantastic in terms of what this offers. So of course you want overlap in some of these wavelengths of light so you can kind of cross correlate to make sure and cross calibrate as well. And as Julie mentioned, you know, Hubble gives you this long time baseline, which kind of helps compare what the new observations will give us. But Hubble also gives the complementary wavelengths, let's say ultraviolet light observations that neither Webb nor Roman can achieve. And so you can then get this wonderful collection of information. Let's say when you're looking at exoplanets, Hubble can tell us things about the atmospheres of exoplanets that you can only detect in ultraviolet light. And that gives you a piece of information that you can connect with the information that, let's say, only the Webb telescope can get out in the deeper realms of the infrared part of the spectrum, and gives you a more complete understanding of the composition of that spectrum. And meanwhile, you've got Roman actually detecting a lot more sources for us to look at and giving us a lot of information. I mean, Hubble's wonderful at following up and looking in great detail at some particular source, but Hubble is, I don't want to use the word terrible, but Hubble is less adept at surveying the sky to find out what's going on in wide areas of the sky. So we're excited about the fact that this Roman telescope will be able to find things going on in all parts of the sky quickly and efficiently, and then we can hone in on, with Hubble, on the details of very interesting objects and sources, and look in the wavelength ranges that only Hubble can achieve to complement what these other observatories are finding as well.
I mean, I could say this suite of space telescopes would be, you know, quite the dream of Nancy Grace Roman back in the 60s.
Sure.
All right,
Very
Grant,
much
one
so.
last question.
All right, I'm going to end it on this because I love this question.
I like your shirt, by the way, Grant. That's a really nice
thank
shirt
you.
got on.
If you are needing computer science majors in the near future, what would you encourage current students or people who are interested in STEM to look into or to go into so they can realistically focus on a career doing the kinds of things that you do, or to support the projects that we have going that are so amazing?
Sure. Well, I'm going to quickly hand this over to the others because I'm not a computer scientist myself, but I know that we rely on people not only developing computer hardware, but developing computer software to handle everything from controlling the observatory, you know, processing commands, things of that nature, to handling these very large data sets. And the image processing, the data processing is particularly important, as well as archiving. I mean, we have, and as was discussed earlier, we have a big archiving challenge coming up, and Hubble already has a marvelous archive, as well as other NASA observatories. In fact, half of the professional papers coming out now that are based on Hubble data are based on scientists looking into the archive of data that's already been collected by Hubble and effectively being able to glean, to use that data. So we need computer specialists who can build both the hardware and the software to enable all of these things. But I don't know if, Julie, you want to be more specific about what you think is going to be needed.
I will interject here for a minute, because that's a common misconception about working where we do or being involved in the sort of things we do. You do not have to be a computer science major to do amazing things and like help NASA's mission along. Like, Frank and I work for the Office of Public Outreach. Obviously, Frank is hilariously more qualified than I am, but we can still take a lot of these things and put them in ways to get them out to the public, to do these sorts of lectures. Like, you do not have to be Nancy Grace Roman to do amazing things in astronomy. You don't. There are many ways and many fields you can get in there and actually be a part of what we do. Sorry, I just wanted to interject that.
Sure. Thanks.
So I think there's two ways to answer your question. The first is if you're a high school student and trying to decide, you know, how do I get involved in all of this? I would suggest don't stress too much about it. Go into any kind of STEM topic, and it's almost always possible to nudge your career in the direction of astronomy and astrophysics if you're starting off with a basis of physics or chemistry or mathematics or computer science. I think that the importance of all aspects of computer science is going to increase, and that's in part because I think one of the frontiers where I think we're going to see some of the greatest insights and some of the greatest leaps forward, or where people can use artificial intelligence and machine learning to have the computers do the thinking for you. That we're heading towards a volume of data, a fraction of the universe that we're looking at, with a frequency that is really beyond the scale for any individual person to look at and identify interesting things. We have to make the computers do the thinking for us. So I think that there's enormous opportunity to leverage the developments in artificial intelligence and machine learning that is informing how Netflix picks which movie to offer me, to instead tell me this is the set of galaxies that you're going to be interested in, or this is something unusual. Go and have a look. So I think that you know, you've touched on what I think could be one of the other revolutions that we see in the next decade. You know, there's access to the data and centralized access to the data, but I think there's also going to be leveraging computers as our partners in finding interest in discovery in the data in a way that we just haven't done before.
Thank you. That's extremely important. That machine learning is growing by leaps and bounds, and it will become more and more important in science as we go forward. All right, so that is it for today. I want to thank you all for these wonderful talks. I want to remind everybody that on November 10th, not November 3rd. On November 3rd, go out and vote. I don't care who you vote for, just get out and do your civic duty and vote. But on November 10th, after the voting's all over, and maybe we have a result, we don't know, on November 10th, come here again, and we will hear from Scott Fleming, Clara Brasseur, and Jennifer Cutler talking about hearing the light, sonification of astronomy data, ways to get at data by listening to it. That will be fun, and we'll see you then. Thank you, everyone. Have a great day.
Thank you.
Thank you.